Chapter 5, Section number 1, Mole Calculations for Chemical Reactions. This is a tough one, but we're going to be all right. You're going to do it. I know you're going to do well. Stoichiometry. Stoichiometry is a fun and funny word. It's also the calculation of quantities of any substances involved in a chemical reaction from the quantities of other substances. Okay. Stoichiometry refers to the ratios. This is a very important word right here. Ratios of substances in a chemical reaction and thus requires a balanced chemical reaction. So the fundamental, maybe most important part about working with stoichiometry is having a balanced chemical reaction. All right, so here we have our balanced chemical reaction. 2P plus 3Cl2 yields 2PCl3. Okay, we've got our states there. A solid plus a gas equals a liquid. How about that? This reaction can be interpreted in two ways. The first way, two atoms. Okay, so we're talking about single atoms. Two atoms of phosphorus, P, react with 3 molecules of Cl2 to produce 2 molecules of PCl3. How about that? How about that? We've got our quantities, 2 atoms of phosphorus, 3 molecules of Cl2 react to form 2 PCl3. Alternatively, you could talk about it on a larger scale. And on a larger scale, what you would say is 2 moles of phosphorus react with 3 moles of Cl2 to produce 2 moles of PCl3. Subtle difference, but an important difference. Now, a flow chart that you can use for mole conversions for stoichiometry problems is basically this right here. You can be presented with the moles of A and use your balanced chemical equation to say moles of B that are needed. Alternatively, you can go from moles of B to Avogadro's number to the formula units of B, then look at your balanced chemical equation, determine the formula units of A, and then come up with the moles of A. We're going to see some of this go down in the next few slides. So this right here is a great question because it says, calculate the number of moles of aluminum, Al, that will react with 3.18 moles of oxygen to form an aluminum oxide. Okay, so what do we have here? We've got a balanced chemical reaction that tells us, and I'm going to use the language of moles because that's what our question gives us. 4 moles of Al will react with 3 moles of O2 to produce 2 moles of Al2O3. Okay, so what we were asking is what number of moles, so number moles of Al react with 3.18 moles of O2. Okay, well our question is 3 moles will react with 4 moles of Al. Okay, so that's a ratio that we can use there. What we can do is we can set this up and we don't care about the products. All that we care about is the number of moles right here of aluminum that we need. So what I'm going to do is I'm going to set this up as a dimensional analysis. 3.18 moles of O2. Then I'm going to use the ratio that I know, moles of O2 to moles of Al. Well, 3 moles O2 react with how many moles of Al? 4. And I'm going to end up with, I'm going to use the old calculator for this, 3.18 times 4, oopsies, 3.18 times 4 divided by 3 gives me 4.24 moles of Al. All right, easy peasy. Now, my next problem gives me a sample of 0.1712 moles of solid KClO3. KClO3 is heated gently for a time, and 0.1146 moles of the compound decomposes into KCl and O2. So here's our reaction. KClO3 breaks down into KCl plus O2. Calculate the number of moles of oxygen gas that are produced. Now there's a couple of different layers to this problem. We're going to get to all of them, but the very first thing that we need to do is get our balanced chemical reaction. And our balanced chemical reaction, well, as it's written, is not balanced. So what we need to do is we need to balance our oxygens. We need to balance those because that's what's really kind of throwing us for a loop. So I'm going to put a 2 in front of here, and then I'm going to put a 3 in front of there. That will balance my oxygens. So I feel good about that. Now, What did I throw off? I threw off my K and my Cl, but lo and behold, put a 2 in front of that. Again, we're balanced. Okay, so we've got our balanced chemical reaction now. But what is it asking? First, they kind of throw some numbers at me. 0.1712 moles of solid KClO3, okay, is heated gently, and 0.1146 moles of that decomposes. So which number do I actually care about between these two? I care about that 0.1146, because what I want to do is I want to find out the moles of oxygen gas that are produced. Okay, well, I know that 2 moles of KClO3 will produce 3 moles of O2. So there's my ratio. But what I need to do is I need to write my problem out in terms of KClO3. I know that 0.1146 moles of KClO3 is what's going to decompose. Okay, so now I need to implement my ratio. 2 moles KClO3 produce 3 moles of O2. All that I did was I took the number that I cared about, the amount that actually decomposes, that 0.1146 moles of KClO3, and I related it to a ratio that I already know. And I'm going to plug all that in. Boop, boop, boop. 0.1146 times 3 divided by 2 gives me 0.1719 moles of O2. And you might look at that and be like, wait a minute. More moles of a gas were produced than the moles of the solid that I used? Is that wrong? Is that right? Where am I? What day is it? Well, this is not a problem. The reason that it is not a problem is because let's look at our ratio. 2 moles of KClO3 are going to produce 3 moles of O2. So it's already in that problem that we see a smaller number of moles of gas produce a smaller number of moles of a solid produce a larger number of moles of gas. Okay. I don't know why I included this slide. We already did this. We're done. We're good. All right, everybody. Let me know if you need any help. You got this.